Hello, everyone. Welcome. Today, we want to learn about derivatives. So, the derivative is one of the main, there are two, if you recall from other what you've learned before, other videos, you talk about the calculus. There are two main parts of calculus, essentially the derivative and the integral. This is one of the parts of it. So, what you've learned so far in calculus kind of led up to this. So, our goals today are to understand, first off, understand the instantaneous rate of change of a function, what that means. Understand how the average and instantaneous rates of change are related to each other. Then we'll learn the definition of derivative, see what's useful, see why we need it, and also how it relates to those things. And also finally, be able to find the slope of the tangent line, which is the derivative to a function at a point. So first off, let's look at something you've most likely seen before, about the slopes of secant and tangent lines. So remember, a secant line to a graph is a line that passes through 2 points on the graph. Let's go over here to the right and just draw a secant line. First, let's draw a set of axes. And actually, I remember, in a second, I need to do something first. I actually need to create some space. Give me just a moment. Make sure I have enough space. Just a bit more, just in case. That should be enough. Okay, so let's go back where we were. So we're going to draw a function, draw a secant line. So first, let's come back and draw our x and y axes. Now let's say I have a function that looks like, let's just make it kind of a, maybe kind of a parabola shape, something like that. So this is our function f of x. Okay, now let's say I want to consider 2 points on this line, this point right here, and this point. Okay, now I'm going to call this point A, this x value, and this is going to be the y that goes, let's just call it f of A. Okay, and this point I'm just call x. So in this case, x can be anything I want it to be, and then here its y value, just going to be simply f of x. And so if I draw a line that goes through both those points, that is a secant line. Okay, I actually should have, just a second, let me actually change the color of that, make it a little more distinctive. So let's actually change that to, kind of a blue or purplish color. Okay, so here's our secant line. Now, that's a secant line, connects any 2 points on the graph. Now, let's go back to the right. Now, if I want to draw a line that touches a graph at only 1 point, that's called a tangent line. Okay, once again, using the same color, if I drew a line that went straight through this point right here and only touched the graph at 1 point, and put arrows in this one as well, that is called a tangent line. Back to black. Sorry, I don't know how that happened. Okay, now what we'll see is, how can I get here from there? Well, if I actually move this point x toward A, what will happen if I move it, like, say, here, and maybe here, and now draw those same secant lines, you can see what's happening is that this is getting closer and closer to the tangent line. Okay, so I move the x all the way over here as close as possible to A, the secant line will actually become the tangent line. Okay, that's what this says down here. So we take this definition of a secant line, which is simply the same as the slope of the line. Okay, the slope of the secant line. And we move x as close as possible to A, take the limit as x goes to A. Could be from either direction. In this case, I chose from the left, but it could be from either direction. Then the limit of that will actually give me the slope of the tangent line. Okay, so the slope of these secant lines, that's what this gives right here, the slope of those secant lines. But then the slope of the tangent line is the limit of those slopes of those. If I limit as this point x is closer to A, those slopes of those lines gets closer and closer to the slope of the tangent line. So I can actually, in a sense, create a tangent line from the secant line doing that. Let's actually see that in live. So let's take a look at something I did on Desmos. Now, this is actually a function we'll use later on, okay, x squared minus 2. Now, so that's the red parabola. Now, this blue line is this. And don't worry so much about how I got this, except this part right here, t squared minus 4, t minus 2. I'll explain that later. That's actually the slope of the line. Okay, so what I'm going to do, if you notice this t is like my x. And I just changed it so since I have my variable as x, I make this t, but it works the same way. What's going to happen, you can see this is clearly between these 2 points, starting here when t is 0, going when t is the same as 2, when x is 2. This point from 0, 2 to 2, 2. Okay. Notice right now my slope of this line right here, the blue line, is at 2. And as I move this closer, this point, as I move t closer to value of 2, move in that direction, notice what happens. The secant line is closer and closer to being a tangent line. Okay. Now, I can't quite go all the way because if I actually go all the way to 2, it'll be undefined. This actually will disappear, but I get close to it. And right here, when it's almost there, you notice it's almost at 2. The x value is almost at 2. And the y value, I actually don't care as much y value, but the y value is almost also at 2. Okay. And then the slope is almost 4. Okay. And that will be important. That's what's happening. So I can start out with a secant line. And as I move that point closer and closer to the point, the other point, one point, the other, is closer and closer to being a tangent line, and the slope is closer to the slope of a tangent line. Now, why is this important? Well, because what we're interested in are basically rates of change. One of the things that derivatives you'll see tells us is the rate of change of a function instantaneously at one point. Let's go back over here. And essentially, we'll do a graph pretty much very similar to what we just did. But let's look at something that will hopefully make sense to us. So let's imagine you have a graph. And along the x-axis, I have time. Maybe it's in seconds, okay? And along this axis, I have distance. And maybe this is in feet. Could be any units of distance, let's choose feet, okay? Let's say you have some graph, maybe it looks like this. Maybe it also has kind of a parabola shape, doesn't really matter, okay? But what this tells you is basically, this is your function f of x, or actually f of t, a function of time in this case. So if this is distance in this axis, so let's once again do a secant line. So if I take these 2 points right here, similar to what we did in the first example, I draw a line between those two. Okay. The slope of the secant line equals what's called the average rate of change. And that's going to be in units, it's going to be in feet per second. Okay. Since this case, think about just the way to do a slope, the slope of a line. Okay, you're changing y over changing x. My y is in feet. My x's are in seconds, so it's feet per second. That gives you, of course, average rate of change then is your speed, is your velocity. Okay. So this is the velocity. But once again, this is a velocity or an average velocity. Okay. Just an average between those 2 points. And like any average rate of change, only takes into account what happens to these 2 points, not what happens in between. Okay. Now, but what if I want to find the instantaneous rate of change? So once again, if I do a tangent line right here at this point, okay, the slope of that line, that tangent line, is that slope equals what's called the instantaneous, just abbreviate the instantaneous rate of change. Okay, instantaneous rate of change. That's the speed exactly at that moment. Okay, so once again, the secant line gives me the average rate of change from these 2 points. All right, but the slope of this tangent line gives me the instantaneous rate of change at that moment. Okay, and the same unit is also velocity. In this case, instantaneous velocity. And that's really important, understanding, be able to find out what the average change at some point is. And we use changes in lots of ways, these kind of average or instantaneous changes. And that's what the derivative gives us. So anything measured, for example, versus time, okay, how much temperature changes per time at an instant, how much pressure changes per time at an instant, or just like your, if you're running, a lot of running apps will have your average rate of speed over some. Basically, they'll often give you both a running app, or if you use that for running, will basically often give you your average speed, your average rate of change, which is your average speed over some distance, some 2 points. Then it'll also give you your instantaneous speed. Okay, and both those are useful. But the derivative, as we'll see, is the same as instantaneous rate of change. Okay, how much something is changing in that moment, in that second, and that's really important for lots of applications. So that's what we're looking for. So basically, we want to start with a secant line like this, the slope of a secant line, and turn it into the slope of a tangent line using the limit. Okay, and that's what's called the derivative. Now, there's one more I want to show you as well. There's another way we can also express this limit, the slope of a tangent line. Okay, this way is much more like what you're used to in seeing in terms of the slope of a line. Base your change in y's over your change in x. This is another way of doing this h of x. Okay, and what that means, let's actually go to another page. Let's get another example. And let's get a thing about the tangent line. There's a set of axes. Let's do a similar graph. Okay, let's probably do some kind of parabola shape just for simplicity. Okay, so let's say this is my point here. Well, let's say this is my f of x right here. This is my x and my f of x. All right. Now, let's say this point here is my x plus h. I'm going to add some positive value h to it. Okay. And then this value right here, this y coordinate for it, is the f of x plus h. So we're doing the same thing. Okay. This distance here is the same as our change in x. This is my change in y. It just looks different. But the idea, as h goes to 0, okay, so right now I have a secant line. I can draw a straight line. Okay. And then as h goes to 0, then once again, we're getting closer and closer to this point. Okay, so if h comes right here, and you get the idea. Okay, there's a lot going on right there, but that's the idea. Okay, as h gets closer and closer to 0, this gets closer and closer to x, and the secant line once getting closer and closer to a tangent line. So it does exactly the same thing. It's written in a different way. Okay, so now let's finally introduce the idea of the derivative. Okay, let's come back over to the left. So the derivative of a function at a point. Let's start there. So the derivative, written this way, the function f of x at some point x equals a, you write it as, read this as f prime of a. This little hash mark right here, like an apostrophe, is one way of writing. You'll learn other ways of writing the derivative in the future. This is one of the most common ways. It's read f prime of a, and that's called the derivative of f at a, is equal to either one of the following limits. And this is the same thing we just showed you here. These are the same limits we just had for the slope of a tangent line. Okay, these limits. Also, it's called m tangent. Slope is also called m. And so they're basically these two limits at a point. Okay, and what that's going to give you then, this is going to give you the instantaneous rate of change at this point a of this function f. Once again, as long as the limit exists and then x is part of the domain. So as long as I have to worry about, basically holes in the graphing like that, holes in the graph, or jump discontinuities, kind of discontinuity, we're trying to avoid that right now. Basically, as long as that limit exists and it's equal to a, then this is called the derivative. A few facts about the derivative. Okay, the derivative f prime a is equal to the slope of the tangent line x equals a. That's what we've been saying. Okay, it goes back to this first graph up here. So let's do one more graph along the same lines. Okay, so it's going to do a similar graph. This is my function f of x. Okay, then the slope, if this is my point A, then slope of the tangent line at A is equal to the derivative f of A. And that gives us the instantaneous rate of change at point A. And once again, as you can see, as you imagine, if you have different points that call a different point A, you will often get a different instantaneous rate of change, a different derivative, a different value. Okay. Now, a few more things about the derivative in general is that once again, the derivative is a slope, so it works just like a slope. Okay, so let's throw in another graph right here. Let's say this is a bit different. Let's say this is our f of x this time, and f of x. And let's put it in different places. Let's say this is our, this is A, this is B, this is C, and D. No, actually, let's do one more. Let's call this D. Let's put in one more right here. Call this D and call this E. Okay. Now, what happens? So basically, since the derivative is the same as the slope of the tangent line, it has the same characteristics of the slope. So right here, okay, at point A, think about the slope of the tangent line. Okay, f prime of A is greater than 0. It's positive. Okay, remember, we have a positive slope, but going up from left to right means the function is increasing. Okay, let's actually go to C next. I'm going to do these out of order. Okay, C, the slope of that line is negative. The function is decreasing there. So here, f prime of C is less than 0. Okay, then we can also have a derivative, just like the slope would be constant. So, for example, here at E, the slope of the tangent line is the same as the slope of the line. It's a horizontal line. So at this point, f prime of at E is actually equal to 0. We have other couple places where it also be equal to 0 at B and D. So notice here I change from increasing to decreasing. All right, here the slope is also, my tangent line is also flat. So at this point, f prime of B is equal to 0. Okay, at that point, I change from increasing to decreasing. And finally here at D, similarly, I go from decreasing to increasing. So here, basically, since my slope is negative here and positive here, it has to go through 0 since everything is continuous. And so f prime of D is equal to 0 as well. Okay, so remember the slope, the derivative is the same as the slope of the tangent line. So it has the same characteristics of slope, and be positive, negative, or 0. All right. Now, so with that background, let's take a look at a few examples. Okay, so I want to find the slope of the tangent line. Let's look at our first slope of the tangent line, derivative, and so forth. Let's look at this first example. So let's say this time my function f of x is equal to x squared minus 2. Okay, if you notice, that's the graph I mentioned here, here as well. Oh, and also let me show you this. I showed this a minute ago, but I also created a graph using this idea of the limit using h instead of as h goes to 0. So here, same graph, x squared minus 2, this parabola. Look at this point, 2, 2. Okay. Now, once again, this is the equation of this line, and the slope is actually right here. So there's my h here and here. So look at what happens when h goes to 0. And once again, the t, I've just had the t set on, that's my x value set on 2. What happens when h goes to 0? So here, starting out at 5. So right now, this has a slope of 9, as you see. All right. Now, let's move h closer to 0. If you notice what happens, as I do that, the slope of that blue line gets closer and closer to the slope of the tangent line at 0.22. You notice if I go all the way, it's undefined because h would be 0. But almost close to it, you see what's happening is basically the same. The slope of the tangent line and the slope of this line are also basically the same. H is almost 0. And once again, as the one I showed you before, the slope is about 4. Okay, that's not a coincidence. That's actually what as we'll see, the derivative will give us. Let's go back and look at a few examples with this one. Okay, so first, let's find, so first, we call this part A, let's find the slope. Well, I actually need a point. So, no, actually what I was doing is fine. So A, find the slope of the secant line. Let me spell that. Do the same thing at that point 2, 2. Okay, so let's go back. We're at the slope of our secant line. Just the slope of the line. Well, I should say at 2, 2, and it's also 0, 0. That's a good place. Or it's actually 0. Let's go back to our picture. Actually, this point, which was right here, 0, negative 2. Maybe I actually believe that point, the 0, negative 2. Okay. Okay. Or actually, we go with any point. So if we just actually follow this, actually, I don't really need the 0, negative 2. They just need this. So the slope, here I'm doing it in terms of x, is going to be, using f of x, is going to be x squared minus 2, okay, minus, it says f of a, so f of 2, okay, and so f of 2 is going by just plug in 2 here for x, 2 squared minus 2, okay, over x minus a, which is 2. So this, once again, my a is equal to 2. And if I simplify this, x squared minus 2, this is going to be minus 4 minus 2 over x minus 2. And that's going to be x squared minus 2. It's going to be minus 2 over x minus 2. And of course, that's going to be x minus 4. X squared minus 4 over x minus 2. Okay, so that's the slope of secant line. All right. Now, what happens if I take the limit of this as x goes to 2? Okay, that's the slope of the secant line. Now, let's find the slope of the tangent line. Okay, so the slope of the tangent line, I need to take the limit as x goes to 2 of this, x squared minus 4 over x minus 2. Okay, now if you notice, of course, here, x can't be 2 or make that 0. I actually make both 0, 0 over 0. Okay, now, but what I can do then is I can actually factor this. Okay, so this is going to be then the limit as x goes to 2. And we'll make this more clear. And so we have x minus 2. This factor is using difference of squares into x minus 2 and x plus 2. Of course, you see these cancel out. This then is equal to the limit as x goes to 2 of x plus 2. Once again, 4 as long as x is not actually equal to 2. Okay, remember, if you've learned about limits so far, okay, the limit, we're just talking about what happens as x goes to 2. Okay, as long as it doesn't, x isn't actually equal to 2. All right. And basically, what would happen, let's actually take a look at that on Desmos. Let's look up another Desmos window. So right here. So what I had was x squared minus 2, minus 4 rather, over x minus 2. Okay. You notice at 2, let's just trace this along. As you can see, it goes to 4. Of course, right there, actually at 2, once again, it's undefined. But that's okay, because the limit goes to 4. Okay, so then that's the same thing you get. In this case, you just plug in 2. And so that's going to be 2 plus 2, which is equal to 4. Okay, that's the limit. So what that value is, this is equal to the slope of the tangent line at x equals 2. And that's also equal to, and that's equal to the derivative of the function at x equals 2. That's equal to the derivative of the slope of the tangent line. Notice that's what we saw in both examples. Let's go back to Desmos really quickly. The examples I just showed you. Oops, it's the wrong thing. There we go. Let's go back to these. Okay. So I showed you here that as we got closer and closer to this point, you know, so said this is the slope. It's actually 3.9. Okay, close to 4. And actually, we could get all the way there. It would actually limit to 4. And the other way, okay, same thing. This basically became 4. Okay, because that's the slope of the tangent line. Also, the value of the derivative for this function, x squared minus 2 at x equals 2 is 4. Okay. Now, let's do a couple more things. I call that part A. I should have called this part B. Now, let's call this part C. You want to find the equation of the tangent line. That's the slope. Okay. So, let's go back over here. I mentioned this briefly. So, basically, the equation of a tangent line, x equals a, is equal to this equation. This basically comes from if you take this, essentially without the limit, and basically solve it for y, which is the same as fx, you get this. Okay, so the slope of the equation of the tangent line, let's come back over here, is y minus f of a is equal to the slope of the tangent line. I should have written that here to make sure this is clear. This is the slope of the tangent line here. The slope of the tangent line times x minus a. Remember, a is equal to 2. All right? Now, we have most of this, but f of a is going to be 2 squared minus 2, which is going to be 4 minus 2, which is going to be equal to 2. Okay, so that point was 2, 2, as we saw. All right? So, let's plug everything in. We have y minus 2 is equal to the slope of the tangent line is 4 times x minus 2, and then just solve for y. We need to find the equation of the tangent line. To distribute the 4 on the right side, we have y minus 2 is equal to 4x minus 8. Then add 2 to both sides. Y is equal to 4x minus 6. Okay. Now, let's make sure that's true. So let's go back to Desmos one more time. Let's go back to this one. All right. So I just turn this off. So my function I'm working with is y equals x squared minus 2. Okay. I'm looking specifically at the point 2, 2. And what I said is the slope of my, the equation of my tangent line should be y equals 4x minus 6. Let's make sure that's right. And yeah, it looks like, as you can see, of course, they're both in blue, but as you see, that appears to be correct. All right, good. Now, let's do one more thing with this example. And actually, I may need to, a second, let me actually go down here and make sure I have enough space. Don't have to add pages later. I'm sure I do anyway. Now, let's go back here. All right, so not quite done with this example. Let's suppose this to be part D. Okay, now, so already found the derivatives. The derivative is 4 at this point. There's also another way we can actually do this. And I want to show you that. And also introduce our last new topic. So introduce the derivative at a point, okay, using this relationship. Limit, that's what we did. Let's actually do it, let's do the limit the other way, okay? So let's back over here. Let's find the derivative. There's actually a couple more before we get this new definition. Let's find the derivative at, once again, x equals 2. Let's use this definition, use this limit. So f prime at a is equal to limit as h goes to 0 of f of a plus h. It looks more like an h. Minus f of a over h. Okay. Now, I already know what f of a is. So f of a is equal to 2. Now, let's find this. F of a plus h. It's a little bit trickier. All right, so we'll just replace x with a plus h. A is 2, so 2 plus h squared minus 2. Okay, remember, function is x squared minus 2. Let's find this. So here, what we have to do is, of course, you can't distribute powers. You have to write this as 2 plus h times itself. That's what squared means. And then FOIL or distribute. And so that's going to be 4. First terms. Inner and outer terms the same. It's be 2 times h. We have 2 of those. So it's going to be plus 4h plus h squared minus 2. And if we combine our like terms, which is like this, h squared plus 4h minus 2. Okay? So that gives us then, go back to the limit. Limit is h goes to 0 of this. And we have to do, still have to do the minus f of a. So h squared plus 4h minus 2 minus f of a. F of a was minus 2. Okay, so this is f of a minus h right here. F of a is minus 2 over h. Okay, keep going down here. And so we still the limit as h goes to 0. Of course, now we're going to have h squared plus 4h minus 4 over h. And on something looks a little bit off. Give me just a second. Actually, give me a second. That something looks a little bit off. So I can get the right answer. Oh, okay. I think I see here. Oh, that should be a plus 2. Okay, there we go. All right. Yeah, so what happened? So here, it should have been, I combined the 4 and the negative 2 should have been plus 2. Except plus, good. Those go away. And yeah, there we go. Okay. That makes sense now. Okay. Back to where we are. It happens sometimes. Just make sure if you think you're doing something wrong, just double check everything. Okay. So now the best thing to do here is just turn this into 2 fractions. 0. And so we're going to have h squared over h plus 4h over h. And the 4h over h, actually, these h's cancel out, and 1 cancels out here. So I'm left, the limit as h goes to 0 of h plus 4. Of course, now, the limit as h goes to 0. This just becomes 0. And now this just becomes 4. And once again, exactly the same thing. Okay, got exactly the same result as I should. All right, so just a different way of doing it, get the same thing. All right, so now let's take a look at our final definition, because basically this is, we can actually do the definition of the derivative as a function. So here is the derivative at a point, okay, a specific point A. We can actually do the derivative in the general sense, doing the same limit instead of using A right here. Go back to using X, and it looks like this, exactly the same as what we just did. Instead of an X, instead of an A. And that gives us a function which would give us the derivative at any point along where the derivative is defined. Okay, once again, assuming the limit exists, and X is in the domain of H. And also it says that functions, if it's what's called I meant to say that if the function, we take the derivative point, the function is called differentiable at that point. And if the function is differentiable every point on some open interval we call I, they say that f of x is differential on this interval I. Okay? So actually do the same thing. Do this really quickly. Let's go back over here. I guess this is probably part E or something. This is part E. Okay. Doing a lot of this one function, but it's a good function to use. All right. Now, this time, let's find just in general f prime of x. Okay. And we're going to here is going to use this definition, f prime of x is equal to, very similar to what we just did, the limit as h goes to 0 of f of x plus h minus f of x over h. This is very similar to what it just did. Okay. Now, once again, so my f of x is once again x squared minus 2. So what I have, let's do this in parts. F of x plus h, very similar to what I did a minute ago. Replace the x with x plus h. So once again, I have to FOIL this, x plus h times x plus h minus 2. If you do that, you could have x squared, and then the inner and outer terms the same. You have two of those, so 2xh plus h squared minus 2. Okay, and so back to our limit, where the limit is h goes to 0. I'll write that better. Of this x squared plus 2xh plus h squared minus 2 minus f of x, which is minus x squared minus 2. As what happens, we have some good cancellation here. And it's going to make this a lot easier to work with. Okay, so still have the limit. Remember, don't forget the limit is still there. Still taking the limit to the last step. Okay, so we have x squared plus 2xh plus h squared minus 2. And now let's distribute the negative, minus x squared plus 2. If you notice, then our x squareds cancel out. The plus 2 and minus 2 cancel out. This is still over h. And so we have left the limit as h goes to 0 of 2xh plus h squared over h. And once again, the best, easy thing to do here is separate this into two fractions. So the limit as h goes to 0 of 2xh over h plus h squared over h. And what parentheses indicate I'm taking the limit of the whole thing. So once again, this is the limit as h goes to 0 of, these cancel out. So we have just 2x. And then here is going to be just plus h. Okay. Then take the limit as to replace h with 0. And so this is going to be equal to 2x. So the derivative of this function is 2x. The derivative of f of x is equal to x squared minus 2 is f prime of x which is 2x. Okay. Now, if we verify something, let's check this with x x equals 2, we did a minute ago. I replace the x with 2, so f prime of 2 is equal to 2 times 2, which is 4. That checks out. Exactly the same results we got before. Okay, so this actually gives us the derivative of the whole function. So anytime, so of course, since is x squared minus 2 is a polynomial, it's defined everywhere. I can plug in any x I want. This will give me the derivative for any x I want. Okay, now let's wrap up with a couple more examples doing kind of a similar thing. All right, we won't do as much with all these, but let's do a couple more different cases. Now, let's do this. Let's do f of, once again, I want to find f prime of x of this function. F of x is equal to the square root of x plus 10. Okay. So once again, we're going to use the same thing, use the same rule. F prime of x, use the same limit. And technically, you can also use the other limit as well. The one that looks more like the slope, but this one is often is easier to use in these cases. So f of x plus h minus f of x over h. Okay. Plug everything in. And so this is going to be, if I plug it in, the limit is h goes to 0 of the square root, is replace x. So we have x plus h plus 10 minus the square root of x plus 10 over h. Okay. Now, this one is honestly kind of weird. Let's make this look better in here. H plus 10. All right, that's what to do, how to proceed. It is honestly kind of weird because it's not something you rarely ever have to do in any other situation. What we're going to do is we're actually doing something called rationalizing the numerator. It's just like rationalize the denominator, but essentially to get rid of the radical up here, because based with that, it's kind of hard to go for it. Okay, so we're going to rationalize the numerator. Okay, what we're going to do then is we'll multiply the numerator and denominator of this function by this, just replace this with a plus. Okay, so it's going to be the square root of x plus h plus 10 plus the square root of x, no, not an h plus 10, this should be an x plus 10, I'm sorry, x plus 10, and the same thing down here, square root of x plus h plus 10 plus the square root of x plus 10. Okay, now once again, the reason why we do that is this is basically a pain to do, is that what that's going to do then is allow us to cancel out the radicals or the square roots up top. And we still have the limit, don't forget that. And so this is going to be, and basically if you either FOIL this, or remember this essentially is difference of squares, what we're going to have then is the square root of x plus h plus 10 quantity squared minus the square root of x plus 10 quantity squared over h times this whole thing. So it's also a bit tedious to write out. So x plus h plus 10 plus the square root of x plus 10. Okay. Getting closer. All right. And of course, you can imagine if you square, that's where that stray mark went, you square a square root, you do what's underneath as long as everything is positive. And so this is still, the limit is h goes to 0 of, up top then we just have x plus h plus 10, same thing here, minus what's underneath, which is x plus 10. Then down here, we still have h, and then times this whole thing. Like I said, does get tedious to write out. X plus h plus 10 plus the square root of x plus 10. Okay. Now we get rid of that and still have the limit as h goes to 0 of x plus h plus 10 on top, distribute the negative minus x minus 10. The good payoff here is actually to cancel some things. The denominator is still the same. H times x plus h plus 10 plus the square root of x plus 10. Okay, so the x's cancel out up here. The 10's cancel out. I'm just left with an h up there. As we'll see, this can work out nicely, although it's taking a while to get here. So finish this limit up. And so then we just have an h left up top. Okay, then we have an h down here. Then we have all this other stuff. Same thing down here, x plus h plus 10 plus the square root of x plus 10. Okay, now if you notice what happens, I can actually cancel these h's here out. And then I'm left with the limit as h goes to 0 of 1 over the square root of x plus h plus 10 plus x plus 10. Okay, now make our limit, just let h go to 0. The h goes away right here. And this is going to be 1 over the square root of x plus 10 plus square root of x plus 10. And those are the same. And so what happens then is this just becomes 1 over 2 of those. There are 2 of those x squared of x plus 10. So 2 times the square root of x plus 10. Okay, and this is my derivative. Okay, so once again, what the derivative does, let's go back up here where I started this one. This function, the square root of x plus 10. So this function gives me, for any x I can plug in, as long as it doesn't make this imaginary, this will give me the instantaneous rate of change of that function at that point. Okay, anywhere as long as, once again, any x base above negative 10 doesn't make the inside of the square root negative, I can do that. So this gives me my derivative. Gives me instantaneous rate of change at any point along that function. Okay, so I get one more. Okay, so 3. Let's find the derivative. Of this function. F of x is equal to 3 over x minus 4. Okay, that's my function. All right, so once again, we use the limit is h goes to 0 of, I think, f of x plus h minus f of x over h. Okay, so let's just plug everything in. So this is going to be the limit is h goes to 0. We want to write an x. H goes to 0. Okay, and so it's going to be 3 over x plus h minus 4 minus 3 over x minus 4 over h. And once again, it looks kind of bad. It's still a bit of a pain, but it's probably not as bad as the one we just did. But what we have to do here then is, once again, we want to simplify. Okay, now we want to combine both of these. Okay, combine these into one fraction. Remember what that means is basically these two numbers here are different since h, since as long as h isn't 0, these are two different numbers. So basically what I'm going to do then is essentially, let's think about the least common denominator is going to be both these multiplied together. So what I need to do then is multiply each one of these by which is lacking in the other denominator. So multiply this one fraction by, which is, instead of just saying it, let me write it out. And we're going back to algebra. So up here we have 3 over x plus h minus 4. Multiply the top and bottom of that by x minus 4. Okay, remember, this whole thing is still over h. Okay, now over here, multiply this one times the one it's missing, which is the other one. Oops, x minus h minus 4. We have the 4 here, times x plus h minus 4 over x plus h minus 4. Okay, now, what we're able to do now then is take this whole numerator, combine it into 1. And so, this is going to be, I'm just going to still have the limit. So 3 times x minus 4 over this combined denominator, x plus h minus 4 times x minus 4 minus 3 times x plus h minus 4 up here over that same combined. In fact, let's put them over the same thing. We have to do as much writing. Okay, these are both over that same denominator, and it's over h. Okay, now let's distribute these up here, and once again, we'll get some cancellation, which will be helpful. So once again, take the limit. Now, this is a bit long. So we stop right here. So if we distribute the 3x minus 12, and over here, minus 3x minus 3h, 3 times h, and plus 12. And this is still over x plus h minus 4 times x plus h, okay? And also, one thing to remember is that you're dividing by h, that's the same as multiplying by 1 over h. Okay, so we're almost there. So notice that these cancel out. Your x's, the 12s. So what we have left then, that stray mark, actually, we're almost, the end is almost in sight. So this becomes still the limit as h goes to 0. So we have negative 3h. Now remember, we have this h right here. H, I'll put out front. Then times x plus h minus 4 times x plus h. Wait, no, not x plus h. Sorry. Wrote that wrong. This would be x minus 4 here and here. Sorry about that. Make sure you see that. Okay. Now, these h's cancel out. So we're almost there. So the limit is h goes to 0 of negative 3 over x plus h minus 4 times x minus 4. Okay. Once again, now, once again, take the limit. So let h equal 0 or go to 0. And so this is going to be negative 3 over x minus 4 times x minus 4, or negative 3 over x minus 4 squared. And that is our derivative as a function. Okay. Now, like the function itself, of course, is not defined. We can't use this. You can't really use the derivative when x is equal to negative 4. Okay, but that's our derivative. So remember, original function was 3 over x minus 4, and this is the derivative. So for that function, this function here, you plug in any x you want except for 4 itself, we give you the slope of the tangent line at that point, at that x value. Okay. Let's go back and take a look at what we've looked at so far. Brief review. So what we looked at is basically talked about the slope of a secant line, or how a secant line becomes a tangent line the closer one point gets to another. And the slope of the secant line becomes the same as the slope of the tangent line in the limit. And then we learned that limit, the slope of the tangent line is the same as instantaneous rate of change of the function at that point, and that is the same as our derivative. And we learned how to find the derivative at a point using these limits definitions, mainly this one. Learned some facts about the derivative, about where it's positive, negative, and 0, what that means, and also learn to find the derivative of the function in general using, once again, that limit. Thank you. Have a good day.